Hello friends, welcome back to another video on this channel. In today's video I will show you how I made this and how you can make yourself an autonomous robot. So the basic principle of an autonomous robot is actually quite simple. So basically it takes the coordinates, its current coordinates using this GPS here, and it also has a digital compass up here which it uses to get its current heading, and then you can put the coordinates of a location where you want it to go using the computer, and basically the microcontroller here just calculates its current position and where it wants to go. It finds out the error heading, and then it uses this motor controller to drive these two motors here and here to move the robot to uh, make it move to the position where you want it to go according to the GPS coordinates. Additionally, we have a 8C05 Bluetooth module here to basically just monitor it using Bluetooth serial. I will leave the link down below for the serial monitor app I am using on my phone. So let me just show you a little bit about this wiring. So first of all, we have the Arduino Mega. First thing you will notice is this wire which is connecting to ground on one side, and on the other side it is going to digital pin number 13. This is just your just to basically stop the microcontroller from moving as soon as you power it on, so you can get it set up and have the GPS here, which is the Neo 6MV2. This GPS get the coordinates and stuff. You can set that all up. Once you're done, you basically just disconnect this from ground and the microcontroller will spring into action. It will then power up the this motor controller, which here is the L298N. This motor controller will then power the two motors. I am using 12 volt geared 150 RPM motors, and I am just using a set of wheels. There's actually a bit story behind these wheels. I'll tell that in just a bit. This is just some normal hardwood board. I've just used two layers stacked up because otherwise this is quite flimsy. Now down here the third wheel is just your normal swivel wheel. I've just mounted it using this piece of wood up here. The entire microcontroller, the Bluetooth module as well as the GPS, also the compass, is powered up using this power bank here. It just plugs in via USB onto the microcontroller, which powers up everything on the electronics side. And then this motor controller, since it needs 12 volts, this power bank as well as everything else is 5 volts, and the compass is 3.3 volts. We are using this 11.1 volt LiPo battery for connecting up to the motor controller. Now additionally, for wiring, the GPS module is wired up into the GPS is wired to serial 1. Serial 0 has to be left open, that is for communication with the computer. The GPS is the Bluetooth is connected to serial 2. For wiring, the GPS is connected onto serial 1, the RX and TX, as you can see, RX1 and TX1 there, pin number 19 and 18. That is the GPS. The serial 2, which is 17 and 16, is the Bluetooth module, and then you have to leave serial 0, that is 0 and 1 pin, open, that is for communication with the computer. There is another serial port free, which is serial 3, that we are not using. However, if you want to add something onto this, you can use that. For communicating to the compass, we are using I2C, so we are using the SDI and SCL. As you can see, this green and black wire is connecting up here, passing on through to the compass here. This compass, by the way, I think I mentioned, I will mention again, this is the GY273 HMC 588-3L. However, a common thing about these HMCs is that they are actually QMCs, so they will not be recognized by the HMC library. This was the case with mine, so my code is running QMC library, but however I will leave the HMC code as well along with the QMC code. So if you get the HMC, so you run the other code. Other than that, one more thing to note about the GPS and the Bluetooth module wiring is that you have to plug the RX of the device module to the TX of the microcontroller, and the RX of the microcontroller to the TX of the modules. Basically, you have to reverse them. Other than that, just power up the Bluetooth and the GPS using 5 volts, and ensure to and connect the compass up there down here into 3.3 volts. As you can see, this is the compass, and This is the compass ground. This one here is obviously the ground for the main microcontroller turning on the motor controller. And then here we have the grounds and ground here, and VCC back there for the GPS as well as the compass, sorry, the Bluetooth. Now for microcontrol, for wiring up the motor drivers, basically we are just using digital pins 2 to 5, as you can see there. So I'm not using PWM, as this is quite a heavy machine and the motors need the full power to run. However, the next two pins, which is 5 and 6, are actually in the code set up as PWM pins, so you can just simply put your values in and connect those to there if you wish. So this on the motor controller here, if you look, there is actually two jumpers, so you just remove the jumpers and connect up the wires on this side to PWM. This one is for this output and this side is for this output. Just connect them up to the microcontroller on these two pins and you can have PWM output. Now if you are using a 5-volt motor system and maybe a little lighter of a car, you can get away with directly powering this guy off of maybe another port on this power bank or something similar. However, I'm doing this other one, basically powering off with this, because this is I'm not really testing in a very like on a paved road. I'm actually going to a unpaved road. You'll see a little bit more about that later on. So that's why I need more higher power motors with more torque and stuff, so that's why I have to do this solution. Now one more last thing about the GPS is, be sure to keep this antenna, this GPS antenna, a little bit higher elevated, and also just make sure that it is clear of any obstacles above it. Like, don't cover it using anything. It actually needs direct view of the sky to properly work. This is a very low powered GPS. It's quite finicky, so it doesn't work well sometimes, especially if there is more obstacles above the GPS antenna and stuff. So as you can see, I actually have it a little bit angled on this piece of wood here, so it just helps it to basically just see this way instead of being covered by all of this. Same goes with the compass. Just use the a big pole and at least like separate it from any other kind of metal by at least 30 centimeters. This I believe is about 60 centimeters or 30, I can't remember exactly right now, but this is more than the required. So just make sure it's at least 30 centimeters elevated from the rest of the electronics. The reason is because these are all basically creating magnetic fields when current is running through the wires, and this compass, the way it works is by measuring of the magnetic field of the earth. Obviously that's how a compass works. So basically it can create interference on this compass, so that's why you want it to be as separated as possible from the rest of the things. Now other than that, basically that's it. So I will quickly switch over to the code. I'll explain a little bit about the code and then I'll show you the video of this in the field. Hello. Okay, so I have switched over to my computer now. I'm quickly going to brush over this code, as it's going to be a very long video if I read all these, explain all these lines of code, channel 35, as well as this part here. This is for your motor controllers. So first of all, let's just start off with the things you might want to know. So first is this one. This is your heading tolerance. This is basically how, like in plus or minus 8 degrees, as long as your compass is reading plus or minus 8 degrees from your target heading, it's not going to try and move the robot. This you can set this to a little bit lower if you have a little bit more accurate compass, or you can move your robot more accurately, and a little bit higher if you have obviously the opposite. Other than that, here we're just using libraries and initializing. This is one more thing you might want to know. This is your tolerance to your waypoint in meters. So as long as the robot is within 1 meter of the target, it will continue to the next waypoint, not try and go any further down. You can, again, based on your GPS accuracy, you can adjust this as you wish. Here is your waypoint. This is where you store all your coordinates. So the first one, this is the first coordinate, this is the second coordinate. I'm just using two coordinates for the test even in the video. That is because of the condition of my ground where I put the robot. It was not possible to move too much. The robot kept getting stuck. I'll show that a little bit more when I'm talking about the video of the robot moving. So I originally planned to do 4, however I ended up just doing 2, 1 straight, turning around and coming back. So this you can have up to 10. In fact, you can have as many as you like. Just change this number to whatever you want. So if you want to have say 1,000 waypoints, if you do, then you can change to 1,000. I have it 10 because I think no one realistically won't want it greater than 10 waypoints. If you want more, just copy this format, just put this curly bracket and then put a comma and then continue up to 10 and change this if you want more. Again, just more setting more float objects and then here serial. This is one more thing you would like to know is this is your input pull-up pin. So I talked about this a little bit more when explaining the wiring of the system. So this is the pin which basically if this is connected to ground, it will prevent the robot from moving. So you can set up the things such as the compass, sorry, not the compass, the GPS, Bluetooth, etc. You can set up everything else, ensure that everything else is correct, and then you can pull this so the robot will start moving. Here you are going to set your calibration. So calibration is done using your own library. So as I said, I'm using the QMC as the ordered and HMC that was delivered at QMC, but I'm using this QMC 583L compass library. Just search QMC 583L compass library and you'll get this one from GitHub. Now here you're just going to use the calibration code here. Just run that, move the robot around a little. uh, just try and do it on its final position as the amount of metal greatly affects the calibration. So just do that and copy the calibration and paste it here, and the robot will be calibrated and your compass will be ready to go. Then you can just here we are just putting the sorry, just putting the waypoint list onto the serial of the computer for debugging, as well as just printing a start. So you know it's going, this all for debugging purposes, not really even going to be ever used because obviously you're not going to have a computer connected to it. That's why we have the Bluetooth. But other than that, here we're just setting some more integers, and this is the part where we read the digital pin. So if you decide to change this for some reason from 13 to some other pin, make sure to change this one too, and both of these you have to change actually. Then here we are just saying if serial is available, that is if the GPS is read, then you have to read the serial and process the GPS. Then here we are just doing more calculations and checking that everything is working as we would expect. This is the part where we check whether the part is connected to the ground or not, that pin 13. So if it is connected to ground, then obviously we don't want the robot to move, and we'll just print in some regular old, we'll just print in some diagnostics. So current latitude, longitude, target latitude, longitude. This is commented out. This is printing your current heading. However, this will not work in this state. It will just freeze the last known current heading, and if it is just you're starting fresh, then it will be 0. The reason is because the compass is being called later on in this other part when it is high. So here it just freezes the compass heading. It's the compass is not actually being called, and it's not actually sending its headings to the robot at this point. And we are just setting the number of satellites in view. And again, if it is high, that is it is not connected to ground, and assuming your current latitude and longitude is greater than 1, that is the GPS is receiving satellite log and it has it is getting your position, then we are going to read the compass, calculate the turn, and move the robot. And we are also going to print more diagnostics onto serial. So we are going to print the current waypoint number, heading, target heading, error heading. This is basically your target heading minus current heading. That is how much you are deviated from the target heading, and your distance to target. If it is not, however, greater than 1, so this else is for this part. If current heading is greater than 1, that is, if it is not greater than 1, then it will be 00, which means your compass, sorry, GPS has not received position log. It will just print in a check GPS error onto your uh, serial, sorry, Bluetooth. Then here we are just processing your GPS, calculating the course to waypoint, calculating the distance to waypoint, and further we are reading the compass here. This is one more part you might want to change if using a HMC. However, I'll leave the HMC link down in the description, the HMC code as well, so you don't really have to mess around with this. But this is one more part where you will have to change this from QMC library to HMC library if you wish. This we are just calculating whether we are at the current waypoint or we need to progress further. If we are at the current waypoint, then we are going to finish sorry, this is the last waypoint. We are going to put a finish on serial and wait for the reset button to be pressed. Otherwise, we are going to move to the next waypoint. We are calculating the desired turn, that is, we are calculating a heading error. If heading error is less than minus 180 or greater than 180 degrees, that is, when it is greater than 180 means like you have to turn more than like basically what it's trying to say is you have to turn more than you have to turn more than like full circle if it is greater than 180. So you're just going to have to set it to plus 360 or minus 360 respectively to make sure it doesn't just keep spinning around, as that is what happens if you don't do this part. Now this, we are just setting some more limits to make our lives easier later on when moving the robot. So if heading error is less than 60 and it is greater than minus 60, we are just going to set it to the error output to be equal to the heading error. So it will be between 59 and the minus 59 here. That will be our error output at this stage. If it is greater than 60, we are just going to set it to one single value, 100. And if it is less than anything less than minus 60, then we are just going to set it to minus 100. This is going to be useful here in this part where it is we are moving the robot. Remember, we called for this up there in the code where we checked for the pin 13. So again, if it is equal to 0, that is if it is less than heading tolerance, your heading error is less than your heading tolerance, which currently is 8, and it's just going to set your error out to be 0. If it is the case, then we are going to move the robot forward. Otherwise, if it is less than 60 and it is less than 0, we are going to move left. Otherwise, we are going to move right. If your error output is equal to 100, then we are going to move sharp right. That is, now the difference, and if it is less than 100, minus 100, we are going to move sharp left. The basic difference between left, right, and sharp right and sharp left is in left and right, we are going to move only one of the motors, and basically it moves the robot more slowly. If it is sharp left or sharp right, we are going to move two in opposite direction to make it move faster and come more. And as soon as it's less than 60, then we are going to just switch over to continue only one motor and get more accurate positioning. Here, this is just your Bluetooth. We are just sending your Bluetooth data and checking for Bluetooth and sending the data as respective. This is your motor. This other code, so this was the main code, and this is the sub, well, like a sister code of sorts. You can say this is where you are going to set all your pins for your motor controller. So these two are your enable pins, that is PWM outputs. However, as I mentioned, I am using full PWM, so these are not connected. And this is your left right motors, and these are your left motor pins. You can mess around with this as you wish based on where you plug it in. Plug the motor controller into your microcontroller. We are just setting all these pins to output here, and by default we do not want the robot to move, so we are just going to set everything to low, and the enable pins are going to be set to 0 PWM. In Berenheti, void Berenheti, which is stop, which was called here, if you remember, they were called at, if we are at the last waypoint, then we are going to call it, and other places up there, such as when the it is connected to ground pin 13. This is just again same thing as here. We're just setting everything to 0 and setting everything to low to stop all motors from turning. Now then we have wide forward, which is setting full power to both the enable pins, and setting the pin 1 of the left and right high, moving both motors on the same direction. Then, as I said, right moves only one motor and the second one stays off. In left, you're again moving the other motor and the second one stays off. In sharp right, we are moving both in opposite directions. Same with sharp left in opposite directions. Just this and this are the opposite of one another. That's basically it for the code. I will now quickly show you the video of the robot working. So this is the video of the robot moving. As you saw that I just plugged out the digital pin 13 from ground and the robot started moving. Now as you see, the wheels are not really suited for this sand, so they keep getting stuck and I have to help the robot out. Now so that is the reason I have to keep on touching it and moving it. However, the robot is trying to move it on its own using the wheels. I don't know if you guys can tell, the wheels keep switching from one to like they keep switching directions and stuff, trying to move the robot. However, because of the sand, it's not really able to move it, so I have to keep helping it. But other than that, as you can see, the robot is working. So first it was kept 90-degree off the heading it's supposed to go in, just to show you guys that it does work and not just move in a straight line. same thing there, as I talked about before, it did that 180 degrees and moving back to the original location where it was. So yeah, that is it for this video. I hope you guys enjoyed. If you did, please be sure to leave a like and subscribe to the channel, and also share this guy with as many people as you can. And yeah, I'll see you guys next time. Thank you.